Hello and welcome back to this series. In this series, we'll be practicing multiple PyTorch exercises. The goal of this series is to get used to PyTorch syntax since it's a bit complicated. Not complicated, but it requires more work to do than TensorFlow. So what we'll be doing here is, this is the first exercise. So what we'll be doing here is the rise type classification. It will be a tabular classification. We'll use a CSV file to do a classification with PyTorch. Later in this playlist, we'll be dealing with images, text, and even more complex exercises such as image captioning or large language models. But for now, we'll start by the rise type classification or the table classification, just to know if it's, just to get used to the PyTorch syntax, and we'll be going into more difficult exercises in the later videos gradually. So the first thing, we'll be using the rise type classification dataset. The dataset is from Kaggle. It's an open source dataset. I'll attach the link in the description. You can find explanation about the dataset here. So we have it's a binary classification dataset, which means that we have either the rise based on some features. It's either Jasmine or Gonin, which is 1 or 0. So I believe maybe this is something related to good or bad quality or something like that. But anyway, we have here are the attributes or the features, which are the ID, area, major axis length, minor axis length, eccentricity, convex area, equiv diameter, and multiple other things together with the class at the end. Before we start coding, we know that ID is something that we need to remove. It's just a number that is assigned to each entry, and usually IDs are being removed from the process of machine learning because they are not representing anything. So it's just a number assigned to one entry. And here is the dataset. So let's go and download the dataset with the same way we have done inside the video that we introduced how to get dataset using Colab. So we'll be installing pip install open datasets -- quiet, which means doesn't print the installation process. It does the installation in a silent process, let's say. And then we'll go into import open datasets as OD, and OD download the rise type classification dataset, which is just the link from Kaggle. So let's start downloading it. Let's make sure first that we are connected into T4 GPU. Usually, of course, machine learning or deep learning things using TensorFlow or PyTorch, better to use better to use GPUs, because the process will be much faster. The training process is much faster with the GPUs. I know this is a tabular problem, CSV file, and not a very huge file, not to be used for deep learning. So GPU may not be a huge deal here, not very important thing here. So, but it's always recommended that you go into the GPU. Okay, so now I provided my username and the Kaggle key. So we had a detailed video about this process. I'll attach it in the description as well, if you want to know more about how we install or how we download each dataset from Kaggle into Google Colab directly. Okay, great. Now in the next cell, we will do our imports. Okay, so let's start by doing our imports. We'll start by importing PyTorch main library, which is Torch, and we will also be importing the NN class from PyTorch library as NN, which means that we are getting torch.nn and giving it such like a nickname or something that we can use instead of writing torch.nn. So we'll use only NN. Stands for neural network, and this one will have all the layers that we are going to use: the linear layer, or the equivalent to the dense layer, the convolution if you want to use any, the LSTM or the long short-term memory, the recurrent neural networks. Any layers will be in torch.nn. Okay, then we will be getting the Adam optimizer from torch.optim. Import Adam. We're gonna use Adam optimizer, and then we will be using also the data set and data loaders object. We will know more about this shortly. From torch.utils.data import dataset and data loader. Then we will don't panic from these imports. Maybe some of them you are not aware about, but it's okay. We will learn each one, the usage of each one later. From torch summary import summary. Okay, this one is to print the model summary, or how the model architecture will be at the end. Also we will import from sklearn.model selection. We will import from this one a train test split. Okay, and also from sklearn.metrics import accuracy score. Now this is a binary classification problem, so accuracy would be efficient here, would be enough. But if it is a multi-class problem, it's strongly recommended that you use precision and recall, as it will be easier to monitor the exact problem of the accuracy. Import matplotlib.pyplot as plt. Okay, so why we are going to need this? We are going to need this because we want to plot the training progress that we will be doing. And then we will import pandas as pd and import numpy as mp. I don't remember that we will be using numpy, but just let's keep it there just in case. Now, next thing is that you have to know that PyTorch does not automatically detect the GPU. Okay, so you have to specify it automatically. Unlike TensorFlow can detect the GPU automatically, but PyTorch unfortunately cannot. So what you have to do is to tell PyTorch that you have a GPU, you have a CUDA GPU. Okay, so we are using Google Colab here, so it's by default, of course, it's CUDA when you choose from runtime. If you choose that one, it's CUDA. This is a Tesla T4 GPU from NVIDIA. This is the CPU. This is Tensor Point. And these ones are available for Google Colab Pro. So you don't need these. We're gonna use the free ones. The free one, device equal CUDA. So you are telling it the device is CUDA if torch.cuda.is_available. Okay, else CPU. So what I'm doing here, I'm assigning a variable called device. Device is CUDA only if torch.cuda.isAvailable is true. So this function is a function that is built in PyTorch. You can go and search for it in the documentation. The function gives true if a GPU is found, and gives false if GPU is not found. So what I'm doing here is that I'm assigning CUDA if this function is true, else I'm assigning CPU. And now let's print device is, let's wait for the imports, CPU. So we don't have a CUDA device available. Let's go and make sure that it's not detected yet. Let's try to run again. Sometimes this happens. Okay, connecting. Yes, now we should run again. And let's give it a moment. Yes, now it's CUDA. So now it was able to detect the GPU. Since this one I already changed before the start of the video, but I think I didn't save. So it's a normal thing that could happen, no worries. Just make sure that the runtime is T4. Okay. Of course, other problems could be that PyTorch was not installed correctly, but we will not go into this. Okay, if you followed the exact description in PyTorch documentation on how to install it, everything will be fine. Also, if you are using Google Colab, no need to install the PyTorch, it's already installed for you. Okay, great. Now we will need to work on our data. So let's start by reading our data set. Data df equal pd.read_csv, and let's get the exact path of the data. So we're gonna refresh here. Okay, so we need to run this again. Okay, that's my fault. because we changed the kernel, we changed the runtime, so we need to run this again. Okay, no problem. Now, when we run this, okay, let me check. And yes, we are good. So here, rise type classification, CSV file, we are going to take path of that file and we are going to use it here. And then we will check the data just by printing the, okay, data.df, just by printing the first 5 rows. Okay, and here we go. So the data is here, looks good. Okay, so now what we will be doing next is that we will do some basic pre-processing. We are not going to do some like a huge pre-processing, because this is not the goal of this series. We will have another videos, I'll upload another videos on how to pre-process the data to achieve better accuracy. But for now, the goal is to get used to the PyTorch syntax and learn how to use PyTorch syntax properly. Okay, so we will be just dropping the missing values, although I don't think there is any, but let's see. In place equal true, so this line drops any missing values, and also we need to drop the ID column, since we mentioned before that ID column is not necessary, okay, is not important in the machine learning. Okay, so dot drop like that, and we will write the ID here, and we will mention axis equal 1, which means that it's a column, not a row. Axis equal 1 means that it's a column. In place equal true. Okay, so this is the first step. Let's print the data shape as well, data.shape, after doing these pre-processing things. So let's, data is not defined, data df. Okay, data frame. So you can see that ID is not found in axis before, because we removed it before, and this line gave an error. So okay, no problem. We can run this again. We read it, and we can run this again. Now we are good. Okay, so we have 18,000, more than 18,000 row and 11 column. Okay, so we can also print data.df head again to see the data, and perfect. We don't have the ID. Okay, just to make sure that we are good. And now let's print the output possibilities. What are the outputs that we are having? So we are expecting 0 and 1 from the data set, but let's also print them if you want. Data underscore df of class dot unique, which will print these values for you, 1 and 0. Also, you can print, if you want, you can print as well the frequency of these values. So it's dot value count, I think. Dot value counts. Okay, so let's see. Yes, perfect. So we have the class 1 is around 10,000, almost 10,000 row, and the other class 0 is 8,200. This data set is not perfectly balanced, but the gap is not that big, so we can proceed. Okay. There are some techniques, of course, that you can handle the unbalanced data set, but it's not the scope of this lecture. Now let's do the pre-processing. Another important part inside the pre-processing, which is the normalization. Why we want to do normalization? So you can see here that the values are extremely huge. Okay, this is not a good thing. Okay, usually we want the values to be small, because the weights of the neural network are relatively small compared to these values. Also, when the weights are being multiplied by the inputs throughout the different layers of the neural network, these values are becoming very, very huge, which means that it will be computationally expensive, slower, and as well sometimes when you are using the loss function to calculate the loss or the error, it may round up the values, okay? Because the values are very big, so it may round up the values. So it's better that we normalize these values. And by normalize, we mean each column, the maximum value of each column will be 1. So how are we gonna do this? We are going to take each column all the values in each column and divide it by the largest value in that column. By this, we have the largest value will be 1. Okay? And we won't, we will not lose anything in the data because we will be doing this on all the data. Okay? Okay, great. Now, first, let's have original underscore data frame equal the data underscore df dot copy. Why we are doing this? I'll tell you. We are taking a copy from the data frame that we have, and we are having it in a variable called original data frame. Why? Because we will need the original values or the old values for the inference, okay, when we do the final inference after we finish all the exercise. Now let's not get into that now, and we can proceed, and at the end you will know why we did that exactly. Okay, you will see why this is important. Now let's get for column in data underscore df dot columns. Okay, so we are going through each column inside the data set, and then we are taking data frame data underscore data frame of that column. So this column is equal to data underscore df of that column divide by what we said, the largest value in that column. Then data underscore df of that column dot maximum. Okay, it's also better that you add absolute value dot abs, but it's not important really because these values doesn't seem to have any negative values, but we can keep it just in case, because of course we cannot see all the 18,000 row, but I don't think there is any negative values, of course, because this is something obvious according to the purpose of this data set, but let's keep it like that if you want. Okay, and then we are going to view the new data frame. Okay, now let's see the result, and here we go. So you see the difference between the values. This is 92, now this is changed, this is 64, this is a change. All of them are divided by the largest column, by the largest row, by the largest value in each column. Okay, okay, perfect. Now let's get into splitting our data set. Okay, up till now we didn't touch PyTorch yet. All of this is just dealing with the data. Okay, so we'll have x, which is the inputs. Can call it inputs, but let's keep x for now, equal numpy array np.array of, so we're gonna convert it to numpy array of the data frame dot iloc, okay, colon comma colon till -1. Okay, what does this mean? This is actually, you are taking data frame, our data frame, you are taking all the iloc means take specific part of the data frame. So we are taking all the rows and we are taking all the columns except the last one. This is means that, okay, this colon -1 means except the last one. Now, because we know, of course, that the class value is the last one, so we are not taking it as an input. Now we will do almost the same with y. Okay, I copied it. Let me show you how. We are going to take all columns as all rows as well, but we are only going to take the last one. So we'll remove this column. Okay. This means, so basically, this means all until. You can think about it like that. And this means only that one. Okay, so colon means all except the last one. Okay, okay, perfect. Now you can run this one. Okay, we are good. Now what we will do is to do splitting. Now we need to split the data set into training, validation, and testing. So you know, training data is for the training or for the model to learn. Validation is to validate the model during the training and monitor its progress. It's the data that is the model is tested on during training, and testing data is the final testing after the model has done all the training. Okay, now let's xtrain. Let's define xtrain, comma xtest, comma ytrain, comma y test is equal to what? Equal to train test split, and we are going to take x as the inputs and y as the outputs, and we will define the test size of our data is, sorry, there is a typo here, test size is 0.3, which means that 70% split. We are going to split the data into training 70% and testing 70%. By default, this function returns 4 values. Great. And then we can do the same, okay, for validation. So let me show you. Let's copy this one. And first, we will need x test here. This is going to be x test and y test. And this one will be x validation and y validation, okay? And then we will be doing, we will be taking the x, we will split the x test. So the goal of our, the goal of this split is to have 70% training, 15 testing, 15 validation, 15 testing. Great. So since we split already the first one for training, we will split the next one for from testing. So we split the original data into training and testing. We will take the testing, which is 30%, we'll split it by 50%. So we will take the x test and y test. Okay, cool. Now let's run. Okay, great. Now we can check the shapes of the data, xtrain dot shape, and we can print it. Let's print xtrain dot shape, and let's as well print x test and x validation. Okay, and great. So now we have, this is 70% of our whole data. This is 50-50. Sorry, this is 15-15, which adds up both to 30%. Okay, great. Now I wanted to add one thing, that we have a repo that is containing all the details about all this lab inside a GitHub repo that is already uploaded on GitHub and having a very detailed explanation of all what I'm doing now. Okay, so you can go through it if you feel that anything is confusing. Okay, now comes the interesting part. Okay, we will be using a dataset object. We will create a dataset object. Okay, why we want to do that? First of all, PyTorch, think of it as a huge ecosystem that has a lot of functions, a lot of classes that can work together in a very seamless way. Okay? Okay, great. Now, how PyTorch understands the data? How PyTorch see the data? It doesn't see it as a pandas. Now the data is pandas or a NumPy array. This is different objects. But we want a dataset, a PyTorch dataset object. Okay? So we need to convert our data into PyTorch dataset object, but we need to specify the details of our dataset or how to access the dataset. Okay? Okay. Now this is not complicated. Okay? Let's follow. Let's start, and you will see what I want to do. Okay. Now we will create a class. The class is called dataset, and the class inherits the dataset object that we imported above. This one. Okay. This is a class. Okay. It's not something it's not a file or something. This is a whole class by itself. Okay. Now the class is having multiple functions. Okay. We will take the functions inside this class, and we will overwrite or modify some of these functions. Okay, so to match the properties of our data. Okay, so what we are going to do exactly here is def __ init. We will define our constructor that takes self. What else it will take? It will take the inputs and the outputs. Of course, this is totally customizable. If you want to change or play with that, feel free to do so, okay? And x, y. So this is taking two things, okay? This is taking the inputs and the outputs. Great. Now, we will have self.x equal torch.tensor of what? Of x, d type equal torch. I'll explain all of this, don't panic, okay, because I know that this syntax may be a bit complicated. Dot to device. Okay, what did I do here? Okay, this whole thing that seems complex, it's not complex at all. We defined the self.x, which means the x, or the input value of that dataset object, will be the x that we got from the constructor, and this is fine. Now, the x we got from the constructor is maybe NumPy array, maybe a normal list, maybe a pandas. So we need to convert it to Torch tensor. So Torch understands the tensors. If you want to deal with PyTorch, you need to have your data as a tensors. So inside this dataset object, you have an inputs of called x. X is converted to torch.tensor. Torch.tensor is something like a list. What will be inside this list? A list or a vector or a matrix, but for now it's let's say it's a vector, okay, because it's a one dimension. Now, how do we know it's one dimension? You can see that this is all the inputs are one dimension. It's not an image or a video or something. And d type is torch.float32, which means that it's a float32 type. And the last part is moving this value to device, which means that we move this list to device. What is device? Device is the GPU, the CUDA device that we defined before. Great. Now we're going to do the same, exactly the same, but with y. So we are going to define here y and here y. Okay? Okay, perfect. Now that's it. That's it for our constructor. Let's go into the next function. We have two functions that we need to modify from the dataset object. Not going to very deep details, but these functions will be used inside the training and how the model will be training. So pay attention to them, okay? The first function is called def_len_self. Okay. Now, I am not naming this function as whatever I want, okay? Because as we mentioned before, the function is already defined and already built inside PyTorch, but we need to modify it to match our dataset and to be suitable for our dataset. So we will do def_len. We are going to return the length of self.x. So what does it do? This function basically returns how, like the shape of the input, okay? Okay, great. Now, def, again, I'm saying these functions can be customizable on your own, okay? But you have to understand what you're doing. Okay, now the next one is def get item. In the same way, it is written like that. I'm not doing it on my own. This is something that you have. This is something from PyTorch. Get item means that we want to get a specific item according to the index. So it takes as well index. Okay. So maybe we need item, like in this table, we need item number 3. So we have to output all these values and the output. Okay. We need the full item. Okay. So we need all of them. So what will we do? We are going to return self.x of index, comma self.y of index. Okay, and that's it. Now we have our class ready. We need to create objects for training, validation, and testing. So let's create them. Let's create them in the next cell so that you don't get confused. Okay, perfect. Now, no problems. Now we create the training. Data will be data set of x underscore train, comma y underscore train. And we are going to do the same with the validation. Let's change the names, validation and testing. And we are going to give it here x underscore val and y underscore val, and then we are going to give here x underscore test and y underscore test. Okay, let's see if there is any problems, and looks good. Great. Okay, now we are done preparing our dataset object. We didn't get yet into the data loader. Okay, so let's start on the data loader now. Okay, so let's start with the concept of data loaders. Now, the data loader concept is an interesting concept. The thing is that when you do the training loop, okay, the problem here is that a TensorFlow is hiding or doing a lot of things for us in the backend, and we don't see that. And that's why TensorFlow is a good thing for beginners. But let's think about how AI is being trained, how any machine learning model can be trained. So basically, you go through all the data, pass it through the model, and then calculate the weights, do the backpropagation, and do all of these things. Okay, but when you go through all the data, how do you go through all the data? You don't go to the data one by one, you go by the batch size, right? Okay, then if we go by the batch size, we need to go into like groups or batches of the data, which means each batch is 8 or 6 or 4 or 16 or whatever you specify the batch size. So to go to the batch size of the data, you create a data loader. A data loader basically is an object that you use to do the for loop during each epoch to loop through a specific amount of batches. Okay? Okay, so let me declare 3 data loaders. So a data loader for each data set that we have. Training data, validation data, and testing data. So let's name train data loader equal data. Maybe if you don't understand it completely now, maybe you will understand it better when we start the training loop. Training underscore data, comma, batch size equal. Now let's specify the batch size as 8. You see here by default it's 1. Okay, so let's specify it as 8. Okay, you can specify it as whatever you want. Okay, and shuffle equal true. We have a lot of course, other function parameters, but we will only use these. Shuffle equal true means it shuffles the data or change the order of the data in terms to avoid biasing. Now let's do the same line for each data set. So we're gonna do validation, and here we are going to do testing data loader. Let's call this validation better. And we are going to put this here and that one here. Okay, perfect. Now we created our data loaders. Now, what is like, how still, if you don't understand completely the data loader, no issue. So let me show you one thing. So for, let's say x comma y in train underscore data loader, print x, and let's print like an equal signs, and print y, then break. Okay, now what am I doing here? I am looping through the data loader. So you remember we specified the batch size is 8, right? Then which means that the data loader loops through 8 like values of, like, it loops through 8 data rows at once. Okay, so each time 8 data rows, next time the other 8 rows, next time other 8 rows, and so on. So when we loop here, we loop through x, which are the inputs, and y, which is the output, and inside the data loader. So here I printed x, and break, I'm just stopping at the first loop so that we don't get the screen full of numbers. Okay, so here you can see print x, it printed x, which means the first row, second row, third row, fourth row, fifth row, up until 8. And the device is CUDA 0, which because we transferred already them to device. And here we printed first label, second label, third label until 8, which means that if we change this to 4, okay, it means that we are looping through multiples of 4 for the data. Okay, like here, you can see 4 rows, 4 labels. You see? That's the purpose of the data loader. So we can keep it back 8, and we can continue our training loop. Okay? Okay, perfect. Now, what's next? After this process, we are going to build our own model. Okay? So we will build the model same way as we built the custom dataset. Okay? We have a model and we will be doing the inheritance of the model. Okay? Okay, let's see. Class my model nn.module. Don't worry, we are going to explain these things. Now we are creating a class called myModel. It inherits from my nn.module, which means that it takes all the functions in nn.modules and all the properties in nn.modules, but we will modify the instructor, of course, the constructor, of course, and we will modify as well the forward function. This is really interesting. Okay, it may seem not to be very interesting now, but I will tell you why. I'll tell you when we reach to the forward function. Let's start by the init, the initialization or the constructor. Now we will write super my model, okay, comma self dot underscore init underscore brackets. This means what? This means that we will use the same constructor of the NN module. So here we created our own constructor from scratch, but here we will use the same constructor of NN module but by using this super, and then we will create the layers. Let's create self.input underscore layer is equal what? Now we need to specify the input layer. Input layer is a normal linear layer. Now linear layer is like a dense layer or a normal multi-layer perceptron. Okay, multi-layer perceptron, one layer of multi-layer perceptron. Okay, x dot shape of 1. What does this mean? This means the number of columns of x, which means that the number of inputs, because the columns are the number of features, which here showing n features. This is the input features. What are the output features? The output features is the hidden neurons. Okay, so how many hidden neurons do you want in the next layer? So you think about it like that. It's something sequential, right? It's going one by one. So the input is how much? The input is 10 rows, 10 columns, and the output is going to how many neurons? Let's say 20 neurons. So this is the hidden neurons. Or maybe better for you that we write hidden neurons and we define hidden neurons up as 10, let's say. Okay? And this is the input layer. Now the next one is self.linear, a normal multi-layer perceptron layer, or we can consider this as the hidden layer. Linear of hidden neurons. Let's wait for the, okay, hidden neurons. And the output of it is what? Is 1. Okay, don't forget, we have only one output, which will be either one output layer, which will bring a probability either less than 0.5, which means 0, or greater than 0.5, which means 1, since it's a binary classification. So we need an activation function between 0 and 1 for binary classification. So self.sigmoid, and we are going to use nn.sigmoid function. You see here nn. I mentioned before that nn is, we use it whenever we want to use any layers or activation functions. Okay? Okay, great. Now we defined our layers. We know our layers. Okay? You can put much more linear layers. You can try dropout. You can try whatever. Okay? But the thing is that now we need to specify the forward propagation. What does it mean? In this function, we need to specify how the data flows inside the model. Okay? How the data goes inside the model. Okay, so the data starts by, the data is x, represented x, and x is equal to self.input underscore layer of x, which means that first it goes to the input layer, and then x, the new x we got is self.linear x, and then x is equal to self.sigmoid of x. and then we are going to return x. Okay, so what did we do here? We created the flow of the data. So first, the data will go to input x, to the input layer. The x will go to the input layer, and then the output of that input layer will go to the linear layer, and then the output will go to the sigmoid layer, and then we're gonna have the final output. Now this is a straightforward flow. It's a normal flow of the data inside the model, forward propagation. But this is interesting when you want to build a completely custom model. You can play completely and modify completely how the data flows inside this model, okay? Okay, great. Now let's create our model. So let's write model equal my model, okay? And we should move it to device. Now, don't forget, everything you're creating in PyTorch, you need to move it to CUDA device, okay? Or whatever device you have. By the way, you can put here MPS if you have a Mac and you set up using Mac Silicon processors, okay? Okay, now we moved the model to device. Let's run this and see. Okay, everything seems good. Now let's create the summary, okay? You remember we used Torch summary. So here we can use this function to see the data, to see how the model will look like in a very user-friendly way. So let's try it. Summary of model, comma, x dot shape of 1, comma. Okay, now let's see that. Great, it's working. Now do you see that? Okay, we have 121 parameters. Okay, let's get to know our function better. This function is called summary. So the function takes the model and takes an input, the input shape. The function in the back end does something like it imagines how the input is, and then imagines a back propagation, sorry, a forward propagation, to see the output shape of each layer and to see the type of each layer it's going through, the number of parameters. It gives you more details. In TensorFlow, we have something like this. It's called model.summary, I believe. I'm not 100% sure, but I think it's model.summary. But you don't need to specify the shape of the input. But here, unfortunately, you have to specify the shape of the input. As we said before, PyTorch needs you to do a lot of work. It's not difficult if you understand the problem, or not the problem, if you understand how machine learning works. It's not a big deal, but you just need to get to know the syntax. Okay, great. Now we have the layers. So layer 1, layer 2, sigmoid, and the output shape is 10 by -1. Why -1 here? -1 here represents the batch size. When we use more data, we will use by batches. So we will use 10 columns, 8 rows, because we'll use a batch of 8. So here it's represented by -1 because it's just a 1 instance, okay? It's a 1 row only. And 10 then linear is getting 1, which means that it's getting 1 output and goes to the sigmoid and gets the final output. Total parameters is 121, trainable parameters is 121, non-trainable parameters is 0. We'll understand these later in the later videos, not for now. And this is the size of the model. Okay, looks good. Now, what's next? Next is that let's create the loss and the optimizer. So the loss function is usually criterion. Okay, it's referred to criterion in most of the references. So nn.bce loss. Okay, I think that's the correct way. Yeah. Okay, now the next one is optimizer is Adam. Okay, now first the loss criteria is nn.bce loss. BCE loss is binary cross entropy loss. Okay, and the optimizer we are going to use Adam. Now we need to tell the optimizers that you will be dealing with that model. So we need to give it model.parameters. which means that we are giving it the weights of the model that this optimizer needs to work on. And also we'll be giving it the learning rate, which let's say 1e minus 4 or minus 3, okay? And that's it. Now we created the loss and the optimizer, and both works fine. Okay, cool. Now let's start the training function now. We are going now into the interesting part. So first of all, in the training, we need to have 4 lists. A list for the total loss of the training throughout the training epochs, the total loss through each training epoch, the total loss through each epoch but for validation, and the total accuracy for training and the total accuracy for validation. Why do we need this? We need to record this after each epoch, and then we can plot them and see if the model is overfitted or not. Okay. Total underscore loss underscore train underscore plot. This is a list for training, and we're gonna have total underscore loss underscore validation underscore plot. And then we will have total underscore accuracy underscore train underscore plot. And then we're gonna have total underscore accuracy underscore validation underscore plot. These are empty lists that will be filled inside inside the training loop. Now for epoch in range of epochs. Now for each epoch in range of epochs. Now we didn't define epochs, so let's write 10 instead of defining. Or let me to make it easier for you, we can write here epochs equal 10, so that you know what is 10 exactly, and then we can total underscore accuracy underscore train equals 0. I'm going to tell you each what is the purpose of these things. Let me write them first. Total underscore accuracy underscore validation and total underscore loss underscore validation. Perfect. Now what are these? Total accuracy training is a number that will be incremented throughout the epochs. It starts with 0, we don't have any accuracy, and after each epoch we will increase the accuracy, and to know after each batch we will increase the accuracy to know and in the end we can know the final accuracy of all the batches inside this epoch, which means all the data. Okay, let's start. For index comma data, or no, let's not use the index is not necessary here. For data in train underscore data loaders, data loader. Okay, you remember data is having input and output. Okay, so we're gonna use inputs comma labels equal data. Okay, we are going to extract data. Data is having 2 values, which is inputs and labels, which are values of 8. Don't forget, inputs is 8 rows, labels is 8 labels. Okay, because the batch size we specified above is 8, and this comes from the train data loader. Great. Now we're gonna need to move inputs. No, we don't need to move inputs to device because we already removed them. Okay. And then we can do the prediction equal model of inputs. Okay, now let's see if everything works still here. It's usually recommended that you stop at some point and try to run the things, because if it's not working, you can have you can easily modify before you continue. So let's see. Okay, this is wrong. Okay, break. Great, it's working fine. And then we are able to do the prediction. Okay, so we have our data, we give the data to the model, The model outputs a prediction, which is definitely wrong because the model just initialized, it's not yet trained. Then we are going to calculate the batch loss is equal to criterion of prediction, comma, labels. Sorry, I don't know what's happening. Okay, and then we can do, let's try to run till here. Okay, you see the error using target size of torch size 8 that is different to the input size of 8 by 1. So we need to make our input having this one. Okay, the input size is 8 only. We need to have it with that shape, 8 by 1. Okay, PyTorch cannot do this automatically. So what we can do is that when we output the prediction, we does this. We does the following. We does a squeeze function of 1. Now let's try, and it's okay, it seems working, but we need to stop it because we need to do a break to stop the loop. Now, yes, working. Okay, what is the purpose of this squeeze? Now, let me print before and after squeeze, and you can understand better instead of explaining. Let's print prediction and print or let's print prediction shape better because it will not fill the screen with very confusing things. Prediction shape and print prediction dot squeeze of 1 dot shape. No, runtime, we need to put a break statement. Break. Okay, let's run. Okay, let me comment this because this is having a problem. Okay, do you see the difference? The difference here is that if we take one instance from the beginning or anywhere, if we take one instance, this is the first one. Okay, we need to break after this one, okay, because it will be better for you to understand. Okay, great. Now, do you see the difference? The difference is the default value of prediction is 8 by 1, okay? The value is 8 predictions, 8 labels by 1. But our after squeeze, it became 8 only, okay? Why? Because when we compare prediction with labels, like in the same cases, guys, in the two cases, the values are same. It didn't change, but we just changed how the data looks like, or the shape of the data. We just changed that, but the data is the same. It's not changing, but we changed how the data is represented because the labels are just 8 rows. It's not, it's just 8 rows. It's not having any problem. But the predictions is 8 by 1. There is an extra dimension. So we need to squeeze it and remove this one to become 8 only. Okay, great. Now we can continue. We can remove that one and uncomment this one back. Okay, now let's remove this break also. Let's go next. Next is, so we calculated the loss. Now we are having the loss. Now we need to total underscore loss underscore train is equal to, sorry, is plus equal batch underscore loss dot item. Okay, okay. What did we do here? Do you see total loss train that we had here? This loss is the loss after each epoch. So after each epoch, we make the loss and the accuracy 0, and then we calculate by adding the loss of the previous batch, of the loss of the previous batch and the accuracy of the previous batch. We keep adding the accuracies of each batch until we finish all the accuracies and the losses, and we have the final loss or the accuracy of the final thing. Okay. Okay, so batch underscore loss dot item means that we get only the number of it. Okay. Okay, so you can think about it that we have 8 rows are being forwarded to the model. We are having 8 rows. We do on these 8 rows forward propagation, and after we do the forward propagation, we compare these losses using the loss function. Sorry, we compare the output with the original output of these 8 rows, and when we compare them, we have the loss or the error. We add this loss to our loss, because this is the loss of only 8 rows, not for the whole data. We add it to the loss of the total loss train, and then in the next batch, the next 8 rows, we do the same, and we add it to the previous loss, and we keep adding until we finish all the batches. We have a final loss value for this epoch, and then we make these values 0 again, and then we do the same process for the next epoch. Remember, you are looping through 2 things. I don't want you to confuse here. You are looping through 2 things, not through 1 thing. And okay, now we have the total loss train. Then accuracy is equal to, how we can calculate the accuracy? We need to calculate the accuracy between the predictions and the labels. So we use the predictions, but predictions here are decimals or float. So we round them to 0 or 1. We use the round function, and we make sure if it's equal label. Now this line will output to you, sorry, it's prediction only, and it's labels, okay? This line will output to you an array of 8 elements, which is having either true or false. Let me show you. Accuracy, let's print accuracy, and break, and break. So break allows us to stop the loop after first iteration so that we don't wait for so long. Okay, just we are still testing our stuff. Okay, we didn't do anything. Okay, you remember we removed the squeeze. So we put the squeeze thing here. Perfect. Do you see this? A list of false, true, false, true, false, false, true, true, which means that the rows are the following. There are 8 rows. And the predictions are, the first one is false, true, false, and so on. Okay, great. Then we want to know how many are true, because this is the accuracy. So we use sum. So let's see, sum will give us what? Sum will give us 3, which means that we have 3 true out of 8. Okay, and then we use dot item, which will give us, at the end, will give us 4. Okay, the number is changing. Don't worry, because every time we start training from the beginning, we start training with the data being changed the order. So it's fine, it's okay. I mean, if it's if you want, we can do it in an easier way here, so that I can show you better. So let me print accuracy, so that the number will be saved and not changed. Do you see the accuracy here? True, false. So how many we have? 1, 2, 3, 4. If we add dot sum, will give us 4. Dot item will give us the exact item 4, which means this number. Okay, it will convert it from a tensor in this strange format. It will give us the final number in just an integer. Okay, so that's it. We will use this way. Okay, so we're gonna copy this one, cut this one, and paste it here. Now, great, we have the accuracy, we have the loss. Now, don't forget, we need to add the accuracy to the total accuracy of the validation of the training. Because remember, this is the accuracy of the batch, accuracy of 8 items only, not for the whole. So we add it to plus equal to this 0, we keep increasing the accuracy. Okay? Okay, perfect. Now, are we done? We are not done yet. We just did the forward propagation, and we got the accuracy and the loss. Now the next part is batch underscore loss dot backward. What does it mean? Now we need to do the backward propagation. Okay, don't worry, there is nothing difficult here. We are going to the other side, or we are going from the other side of the model to do the backward propagation. And at this point, the optimizer will come. So we need to do optimizer dot step, which means optimizer, please take a step and change the weights because we already have the loss. Optimizer dot 0 underscore grad. Okay, what does this line means? Means that after the optimizer changes the weight in this batch, the optimizer restarts again. This avoids having writing this is better for not having like the model will converge by that way. If you didn't do that, the model will not progress. Okay. Okay, perfect. Now we are done with the training. The training is working perfectly fine. Okay, let's try to do one batch of training and it's working fine. Great. Now the next part, guys, is the validation. Okay, we have a validation data set. We want to do a validation. Okay, now validation means that we make the model after getting trained. We make the model does a prediction, and after this prediction, the model will not do a backwards propagation. It's just a prediction. You are testing the model during the training. That's it. Okay, you are doing a test of the model, but the model is not yet trained. Okay, okay. Now with torch dot no underscore grad, what does this mean? This means that with torch dot no grad means that use the PyTorch model, but not for training, just for testing. So it basically it prepares the model for doing a prediction, but without changing the weights. We will just do the prediction. It's like we are using the model for inference. Okay, for inputs, comma labels, or no, let's put it the same way as we did before so that you don't get confused. In validation data loader, we are going to have inputs, comma labels from data, and then we are going to do prediction equal model inputs dot squeeze the same way. Okay, we are doing everything the same. Okay, in fact you can copy the same code up into here, the same code, that one into down, but without these three lines. Okay, but of course total accuracy will be validation, loss will be validation. Okay, then we calculate the loss. The loss is used here just for seeing the progress of the model, and it will not be used for backward propagation. Okay, just want you to keep in mind that. Labels, and then we are going to have total underscore loss underscore validation is plus equal batch underscore loss dot item, then accuracy of we are going to do accuracy is equal to 2 brackets like we did above, so we can take this copy, no issue. Okay, and everything is same. Then we can write the total underscore accuracy underscore validation is plus equal accuracy, and that's all. Okay, now we are having the validation part. Okay, okay, great. Now let's try to run this and keeping the break function. Okay, break, let's see. Okay, and perfect, looks good. Okay, so everything is working. Of course we'll remove these breaks at the end, but for now we just want to make sure that the code is working without any errors. Now we can remove them. Okay, no problem. And we can go back and write inside a epoch level, not a batch level, because remember here all of this is batch level, and this one as well is batch level. Okay, so means that you have two loops, you have nested loops, don't forget. So we are going to the main loop now. The main loop is the loop for the epochs, and we will start appending the values for plotting. We're going to append total loss train plot dot append. You remember the lists we created here. Okay, dot append round total underscore loss underscore train divide by 1000 comma 4. The comma should not be here. Yeah, comma should be inside. Okay, I'll explain this to you, don't worry. Now let me do the same for all of them. Now let's change the lists. Total loss validation will be here, and we will use total loss val, and then we are going to use total accuracy train, total accuracy train. We are going to use, okay, now how we are going to use the accuracy? Accuracy will be a number, okay? So the number should be, okay, let me show you. Total underscore accuracy underscore train multiplied by training underscore data dot underscore get underscore item underscore like that. Okay, multiplied by 100 comma 4. Okay, what did I do here? Okay, it's nothing, it's just the percentage formula. So actually I'm using, in the first one I'm using the round function, okay, to do the following. I'm taking the loss. The loss will be a very large number, okay? It will not be that large number, but it's still, you see here, total loss train 676.150. Okay, it's better that we divide the loss by 1000 so that it will be normalized. We are taking the same concept of normalization here. And round comma 4, we are using this one to do the rounding part, okay? So we take only 4 numbers after the decimal, not more than that. And then validation, we are doing the same, but with the total loss val. Accuracy, we are doing the percentage formula. So we are having round total accuracy train, with the total accuracy we got from the training, divide by training underscore data dot, sorry, it should not be get item, it should be get len, I believe. Len only, without get len. Len. What is this? It means that we get the length of the data that we have. Okay, so the total amount of the data we have. So if, let's say, if we have 10 rows, we got 6 correct. So 6 divided by 10. Okay, and then multiplied by 100, which will give us at the end 60%. If we take the example. Okay, so we are calculating the percentage, and we are doing round 4 as well to take only the first 4 values. Now we can do the same with the validation train here, and you can see here that the total accuracy will be for validation, and this one is going to be validation underscore data dot len. Okay, do you see now the good thing about using the data loaders, about using the dataset objects, about using the things that PyTorch provide? You feel that the things are totally customizable, and at the same time, everything seems useful and working good together. It's, as I told you, it's like an ecosystem, okay? Okay, great. Now we can print the stuff, okay? So let's print the things. Print epoch number, okay? And this will be, let's put it like that, epoch +1, because it starts from 0 and we want to print it in a very nice and neat way. Train loss is, we are going to take that part for the train loss. Okay. No, not the total loss train. Yes, we are going to take that part here. And then we are having the train accuracy, which we will take this one also, training accuracy. Do you see that one? You see what I'm doing? Okay, I'm creating the loop. I'm creating the print statement for the training, okay? And maybe we can put a line, okay? So let's put 3 quotes and 3 quotes, and we can put a line for easier writing, and then we can write validation loss is equal to, we are going to take this one and validation accuracy is going to be this thing between curly brackets. Okay, you can print it in any way you want. Okay, this is not something this is not a problem. You can even skip the printing part. Okay, this is just for giving some good look, and you can see the progress. So let me print also after each epoch, can print maybe 25 equal signs. Okay, and let's try to print the training loop. Okay, yeah, perfect. Now you can see here that the training is started. Okay, the training is very good actually. Okay, and it's not changing that much, you know, because it's the data set, the model needs modifications, the learning rate maybe needs to change. So don't expect the model that it will be very good, because we should have like a whole session for optimizing the model and making it better. Okay, now maybe I can change the batch size. Maybe you can make the batch size 32 and we can try again. So 32, 32, 32. Let's run everything again and let's see the model progress. So it starts from the beginning and it increased up till 98.71. Okay, so okay, it's good. The model is good. As I told you, you can play with the model, you can optimize the model. The goal is for the PyTorch syntax. Okay, and that's all. Now we can proceed with the testing. Now we can see that the difficult part has passed. Start with the testing. Okay, so in the testing, we will use the testing dataset to test our model. Okay, so let's see. Now we will start with torch.no_grad. As well, this is the same part as what we did for validation inside the training loop. And then we will write total_loss_test is equal to 0, and total accuracy test is equal to 0. Okay, and then we will do the for loop for inputs or for data in testing_data loaders. We will be having inputs, labels is equal to data, and then we will have predictions. Prediction is equal to model of inputs. Same way we are doing, everything is same. Inputs dot squeeze of 1. Then we will write batch_loss_test is equal to criterion, the same loss function we were using, of prediction, labels dot item. We are going to take the item of that one. And then we are going to have it, because don't forget that this one is also batches. Okay, we are doing this as batches. Now you can have it as batch 1, doesn't matter, but we are having it the same concept as we are doing for validation. So we will add it to total loss test. So total loss test is plus equal batch_loss underscore test. Great. And then we are having accuracy the same, so maybe we can get the accuracy also here and that one here, and we can change accuracy prediction same, but this one will be here. Okay, and that's it. So I believe nothing is missing, so we can print accuracy, the testing accuracy is round. Also we can do the same round of, okay, we can get it from up here. Now we have to be efficient. You can get it from here, so you don't waste more time. Okay, and write it here, but this one instead it will be accuracy test, and this one will be testing underscore no, not testing underscore data dot len by 100. So you can see here that testing data loaders is not defined. Okay, testing data loader it's supposed to be, I think. And it, yeah, perfect. Now the accuracy is 98.79%, which is amazing, of course. And this is, you can think about it, this is a small data set, small model, not a very complex problem, so it's not difficult to get a very good number of accuracy. But still you can play more with the hyperparameters, with the network, with the things, and you can get better results. Okay, now comes the visualization part. Okay, so first let's create figure, comma AX axis is going to be a plt.subplots. We'll explain this, no problem. Number of rows equal 1. Sorry, equal 1. Number of columns equal 2. And figure size, fig size is equal to 15 by 5. Now what I'm doing here, I'm creating a plot. Okay, two plots. I'm creating a figure. The figure is having one row, so one row and two columns. Each column belongs to one plot, and this is the figure size. Okay, it gives me the figure and the axis. Now I will write the first axis of axis 0. I will plot here what I will plot the axis 0. So it brings the screen like a grid. Okay, like one row and two columns, and the first row, the first column, I'm dealing with it with this one, axis 1, axis 0 dot plot. What I'm going to plot here, I'm going to plot total underscore loss underscore train underscore plot. This was the list we got from above, you remember? Label equal training loss. And then I am going to have axis of 0. I'm going to put some labels and put these things later. So, but for now, let's put this. This is the training loss, and I'm gonna need the validation loss, total loss val. Then we can put the labels. So dot set title. Now these things you don't need to memorize, okay? Because you can get easily these things from Google, not a problem. I think it's called validation. You can get it copy paste from Google, but you have to understand these concepts, okay? And then you can search for the things in Google. It's fine. Training and validation loss, maybe let's say over epochs, maybe, okay? And then we can write axis of 0 dot set X label. What do we want on X label? The X label is going to be the epochs, okay? And we are having as well the Y label, same, almost same. Just change this to Y. And we are having loss as the Y label. And then I think it's pretty clear when you write it, okay? I advise you that you rewrite the exercise again, even if it's on GitHub, but you rewrite it again. It's better, so that you practice you practice the structure, this structure, okay? And you can set a limit as well. Axis of 0 dot set underscore Y limit. Okay, why do we need Y limit? Because we want to specify where Y should stop. So let's put Y between 0 and 2 maybe, okay? And axis of 0 dot legend, okay? Okay, now that's it for the accuracy, for the loss. we're gonna take the same and we are going to put here 1, axis of 1 in all of these instead of rewriting everything again. Now here we will plot the accuracy. So total accuracy and total accuracy. We're gonna rename it here to accuracy. I'm gonna take this into here and epochs accuracy, and the limit will be 1 to 100 because accuracy is in percentage, and we're gonna write here accuracy. And that's it. We can do plt.show. Now let's see the results. And expected n calls. Okay, I believe it's without an underscore, I think. Let's see. Yeah, perfect. Now we have the training loss and training validation. So you can see here that the validation, the training loss, training validation. So you can see here that there is no overfitting, and the model is going good, quite good in training loss, but the validation, the red line is not shown. I'm not sure why, but let's see. Let me see the accuracy. Accuracy is almost same. So I think it's showing, but maybe it's not very clear. So probably we need to set the spacing between the diagram or something. I'm not sure, but let me try to put 50. I'm not sure. I'm trying this together with you, but okay. Anyway, it's not the problem. It's not that problem now because it's not showing here total accuracy validation plot. Okay, let me see. Am I total accuracy validation plot? Yeah, I didn't append it. Do you see here the problem? It's an empty list. I didn't append it. That's my fault. Sorry guys, that's my fault. So let me see here. It's not total accuracy validation plot. Should be that one. And we can run the training again. And then we will have some results here. Now the training already now it's running for the second time, so there is no increase. Maybe you can run again from here and you can see difference. But okay, let me run again to see the different plot. So we can run here loss and optimizer and these things. And the training loop, yes, it's starting from the beginning now. And we are checking the accuracy again and run that one. Okay, let's make it from 0 to 100. Okay, let's see. Yeah, now it makes sense. Now there is no overfitting and the other line appeared. So do you realize the problem? The problem is that I didn't fill this list. I didn't append any value to this list, as I appended accuracy training and accuracy validation inside the same list, which came as wrong, obviously. So that's my fault. That's a typo, but luckily it was not a big deal, not a big problem. And that's it. Now we are having already the training. Now, what if we want to do an inference? So we want to use our model in production, okay? Or we want to use it on a mobile app, or we want to use it in whatever. I want to do one single prediction. I don't know the result. I want the model to know the prediction for me. So let's say we have area of whatever, 6, maybe this number. Okay, I'm writing just random numbers. And we have measure axis length. Okay, now comes the thing, okay? Before we write these things, you remember the original df? You remember that? This we will be using to do the normalization, because we did the normalization using the same values from here. So we will use it to do the normalization again during the inference. So how are we gonna do that? Let me show you. Now we will write area equal a specific number, any number maybe, I don't know, that one maybe, and we'll write original data frame of area divide by original data frame area dot max or dot absolute. We did the same, dot max. And we are going to do the same here with measure access length. Let's write any number, maybe 81, and we put this one here. And then we are going to do the same here, measure minor access length. 42, let's say, anything, doesn't matter. Okay, and do you see what I'm doing? Now, these numbers, as a user, you should insert these numbers, and at the end, you will find the prediction. So you can put, let's put more things. Let me take it from the data frame, so it would be better just copy pasting. Okay, minor access length, and this thing can write here 32, and convex area we can write here let's say 12. Sorry, need to copy this, paste it here, and so on. You can continue with this process. Let me write it quickly. Yeah, this is missing this thing. Okay. Let me put. Okay, and then we will have more columns. So let's write these. Okay, let's take after convex area we have this diameter. Put maybe 33. And then we have extent. We put, let's say 98, and then we have perimeter. We put 927, roundness, and we put this as maybe 677. Now any numbers, that doesn't necessarily. I just want to show you the final result on how to do a prediction, okay, without using the dataset. Okay, and maybe we can keep 24. Okay, and that's it. Now we're gonna use model.predict, or we can only use model. No need to use predict. Predict is used in TensorFlow. Can use model only, and we can take these values inside the list here. Area, measure access length, minor access length, this thing, convex diameter. I know this may takes a little bit of a while. You can skip this section, by the way, no problem. But this is just for you on how to do the final inference, okay? Roundness, because it's important to know how to integrate this inside a mobile app or a normal software. Okay, now that's the list. Don't forget, what did we do inside the data pre-processing part? We did the following, okay? Now, we can do the same, actually. We can take the dataset object and create it, or we can create without the dataset object. Since you already know how to create the dataset object, we will do it without the dataset object. Okay, now we converted to tensor, and then we moved it to device. Because the model is on the device. Don't forget, the model is on the GPU, it's not here. It's on the GPU. So to use these values, you need to move them to the GPU. So let's do the same. We are going to have a list. We're going to do torch.tensor. We are going to have dtype equal torch.float 32. And then all of this tensor, we are going to move it to device. Same way we did in the dataset. Okay, and that's it. Prediction equal, or let's call it my prediction equal, and then run. And here we go, working fine. My underscore prediction. What is my prediction? My prediction is 0, which means from here it's not adjustment, it's going in or this thing. Okay, and we can do dot item to get the tensor that is only 0, and that's it. So sometimes this number can come as a decimal, okay, which may be 0.70 something. Okay, you can use the round function always, so you can do like that, round, and here you go. you have 0. Okay, so this is important that you use it if your output is something like the 0.73. is the same way we used above. It rounds it to 1. Okay. Okay, that's it for this lecture. So you are going to find the repo for this complete exercise explained in very deep details on in the description. You're going to find as well the other videos, the video related to how to use the datasets inside Colab directly, and also the video on how to install Python and IPython or the Jupyter notebooks in case you need to work locally. I always advise that you work on Google Colab, but if you want to work locally, make sure you install CUDA properly. Okay, that's it, and thank you for watching. Subscribe and like for more videos like this. Thank you. If you have any ideas, specific ideas in mind that you want me to implement, please write in the comments. Thank you.